Hello everyone, welcome back to Native Engineering once again. Today we are doing an exercise on shear stress, and the exercise reads as follows. Figure 1.21 shows a tie bar fixed with a pin to a steel member. A load of 100 kN is applied to the tie bar. Calculate the shear stress developed in the tie bar. The thickness of the tie bar is 15. And this is the structure that we are given. We are having two bars. We have this object and we also have this object. They are tied together by a fixed a pin, which will be this portion right here. And then there is a force of 100 kN. It's applied to this bar in that direction as the arrow it's pointing. And then we are asked to calculate for what? For the shear stress that will develop on this member, or this on the section where this object is going to shear. We know that shear stress is given by force divided by area. We already know the force that we will be dealing with, which is the 100 kN that we are given. The trick when we are dealing with these kind of questions is to get the area that is the one that we are going to put here. We have to get the correct area, in other words. So what is it that we know or remember about shear stress? Is that the force will be parallel to the area that we are dealing with. So we go back to the diagram. We are pulling this object. Let's say this is object number 1 and this is object number 2. We are pulling object number 1 to that direction. Object number 1, which is pinned using this pin to object number 2. So what's going to happen? Let's say the pin is strong enough to withstand the force that is being applied to it in such a way that it's not going to break. So where will object number 1 break if it were to break? This is the pin that we are dealing with. The pin will cause object number 1 to break somewhere here. And we know that the area that we will be dealing with must be parallel to this force as it is being applied to that direction. So we are going to say this portion will be taken out. This portion will be taken out from object number 1. What will that portion look like after it has sheared, or after it has been separated from object number 1? It will look something like this, with that being the side that we see from this view, and then it will be something like this. With this side being the side that has sheared, or the side that the object separated, where the object separated. And we know we are given 60 from here to here. It's 60. And then we are fortunately enough that they also gave us the thickness of this material, which is 15. That 15 will go where? From here to here. So now we do have the area and we also have the force. Let's check. Is the area parallel to the force that it's causing it to shear? The force is applied to that direction, which is, yes, parallel to this area that we are dealing with. Therefore, we are going to do the calculations. going to erase this. We'll need that. Let me just erase this. So we know area is calculated by what? Force divided by area. What's the force? 100 times 10 to the power 3 divided by, what is the area? 0.06 times 0.015. This is the area that we are dealing with. But notice that the object shared in two places. It shared in this position and it also shared in this position. The areas are the same, yes, but we have to indicate that the object has shared in two positions. So we are going to say, after calculating our area, because the area of this object here is equal to the area right below this object, we are going to say times 2 to indicate that two sections separated from the original object, which is object number 1. Therefore, from there, we are going to get our area, which is equals to 5.56 megapascal. And that is how we go about calculating for a shear stress. Make sure that the force it's parallel to the area that you are going to put here, if it is shear stress. And that will be all for today's video. I will see you on the next one.